3 more things today. And I'm hoping to finish up a little bit early because I have somewhere to run off to. But we'll see. We'll see how long it takes. We want to search. We want to remove items, and then we want to expand this to do something called a map. Let's start with searching. And we'll do that by way of a Boolean method called contains. So basically, it'll return true if the value is in the tree. It'll return false if the value is not in the tree. So, just like everything else, I'm going to accomplish this by first remembering my Java keywords and using a recursive method. So, I'll call this one subtree contains. And value and root. So pretty much just like everything else. By now, hopefully, you're beginning to sense a pattern. Private Boolean subtree contains okay. Here, we also have 3 possibilities, though they're slightly different from the 3 possibilities in the add method. The 3 possibilities are that the first one is that subtree is null, in which case this subtree does not contain the given value. It's null. It can't possibly contain that value. So that's a pretty simple implementation. If subtree equals null, return false. Done. Next case. Subtree's left data or data left or data right is the value that we're looking for. In which case, in either of those cases, we return true. So if subtree dot data left, now we can't use that because that will compare references. But because we say that whatever E is comparable, that means it has the dot equals method. And likewise for data right. Now the third and more complex option. The subtree is non-null. Its data left is not the value we're looking for. Its data right is not the value we're looking for. However, it still has subtrees that we can search. So, and because this tree is split into regions defined by whether the values are greater than or less than data left and data right, we can pick the appropriate subtree to search. So, if subtree, we'll use basically these same comparisons. So let me grab exactly that. and it'll return, does that subtree contain value, and this would be subtree dot all the way on the right. Else if it's greater than data left, return subtree contains value subtree dot middle. What is my else going to have? And that's it. Let's see if it works. Let's pick one that does exist, for instance 11. So that should be true. And this should be 17. That should be false. Right. And we get the result we were expecting, true and false. We wanted to do some removal as well. So let's remove an interesting one. So let's remove 11. Then print it out. Obviously this won't compile because we don't have a remove method, but we can fix that real quick. And this remove method shouldn't return anything. Remove some value. Now, our remove from subtree method will look remarkably like this method, so I'm just going to go ahead and copy and paste it. It's void. Remove from subtree. We also have options here. If subtree equals null, that means that the value doesn't actually exist in the in the tree. We're removing something that isn't there, so we don't need to do anything. So here, it's possible that data left equals the value, in which case we actually have two possibilities. Either data left could be the only value in this node, or there could be a data left and a data right. If there is both a data left and a data right, things get a little trickier. So let's start with the simple case. If data left equals value, it is the one we're looking for. And the easy subcase is if subtree data right is null. And if that's the case, that will accomplish removing it. Otherwise, what do we have to do? Let's say, for instance, we want to remove 23. This gets real messy. Because now 42 is the only element in that node, but we also have all these subtrees to worry about. So what actually has to happen is that some values need to move around. And in fact, that is quite a difficult problem that is introduced by having 3 branches and 2 data points in the same node. And this problem right here is exactly the reason that binary trees work out so well. Because in a binary tree, a node is either there and has one value, or it is not there. There's no crazy in-between state. So I'll just comment this out and say this is hard. We have to put something for the else. And return. Of course, the problem is that if data right is null and we set data left to null, now we have a node that is completely null. It contains nulls, which means that we should get rid of that. Get rid of that node. So I'm actually going to do something along the same lines as what we did for add with the pass-through thing. So wherever we call remove from subtree, we will do that. Here we should simply return subtree. If subtree is null, we can return null. It doesn't matter. And now here we have we really don't have to change much here. Figure out what subtree contains the value, and then what's my method called? Remove from subtree. Okay, there's this one case that we haven't dealt with yet, and that also involves some moving around of data. So we'll say here return subtree and make a note that this is really hard. So I will make sure I remove things that don't fall into those cases. I think I'm removing 11, and that'll work out fine. That will only execute that case. Should anyway. This needs to return a tree node E. Uh-oh. It did something I didn't want it to do. It somehow returned a null. Okay, so 11. This is not null. It's not equal to either of those pieces of data, so it should go down the left subtree. That is non-null. It's not either of those pieces of data, and it should go down the left subtree. Aha! That could be an issue. This shouldn't return that. This should be subtree.write equals subtree dot middle equals and subtree dot left equals. And this should simply return subtree. Right, now I think we're on the right track here. And that looks a lot better. 12.8 with no 11. Perfect. Okay, questions? Okay, so how do we turn this into a dictionary? Sorry, a map. Java calls them maps. Every other language calls them dictionaries. So I'm going to copy and paste that into a new file and change the name of it to map. I'm not going to call it tree map because that is actually the name of the class in the Java framework that does exactly what I'm about to do. And I will use this trinary tree stuff, still leaving out the parts that I said were really, really hard. For the programming assignment, you just need to implement a binary tree, and it does need to act as a dictionary sort of thing. The difference between just a straight tree and a tree that acts as a dictionary is that instead of having just a single generic parameter, e, it has two. It's storing a key and a value. A dictionary in most languages and a map in Java stores key-value pairs. Keys are unique. You can't have the same key in you can't have two copies of the same key in the map, and each one basically serves as a reference, some sort of lookup for some other object. In the programming assignment, we'll use it to look up the line number, basically, the instruction number for a particular label, which means you don't get to ignore things that start with colons anymore. Since I already have E all over the place, I'm not going to change that. Normally when maps are genericized, one generic is called K for key and the other one is called V for value. So I'll go ahead and say V. And that's the syntax for multiple generic parameters, a comma in between. I'll change my node so that we also have a key and a value. And now this node has both a key and a value. A key left and a value left, a key right and a value right. So I'll change data to key. Now in a map, all of the comparisons are done on the keys. So the values are kind of just stored there, and the keys is how you actually manage this information. So if you go looking for something in a lookup table or a map, you look it up by key. So we'll actually implement a get method in a minute. But for now, actually for sake of time, I'm going to leave those names data left and data right. In an actual implementation, a better name for those would be key left and key right, if I were writing this from scratch. And that's how you would accomplish all the logic is still the same, just operating on keys instead of a singular piece of data. We have three operations right now: add, contains, and remove. Remove operates on the keys, so we don't actually have to change anything there. Contains operates on keys, so we don't have to change anything there. Add specifies a key and a value. So it's basically add this value with a given key. So we'll change that name and the value. So key and value, and then this method will take a key and a value. And the only difference is that when we actually store this information, not only do we store the key, but we also store the value. In these calls, I also need to specify value. And there's another thing I have to change. So I set the value there, both the key and the value. Here, we're migrating the key over, but we also need to move the value over. And then save the value. Here we now have multiple statements here, so we should put some curly braces in. And subtree dot value right equals the value that we have passed in. Emacs bindings do not work in here. Okay. And everything else, I think, is good. I'll make it look remarkably like what will be in the homework. You'll create a map of strings that point to integers. So my map equals new map string integer. My map add. I'm going to modify the subtree as string to not only print the key, but also the value. And yes. Don't forget to modify your generics everywhere. The downside to doing copy and paste. In general, I recommend avoiding copy and paste at all costs. finally. Okay. So now we run this and prints out a tree and then hello and new. Not a very interesting map, but you get the idea. Let's see if I can put something in between them. Int. And there's the map. So now for a get method. It's going to be very similar to contains. And really the main difference is that with the contains method, we're concerned with whether or not, in this case, and in normal map cases, we're concerned with whether or not the key is in the map. With a get method, we want the value for that key. So, kind of going a little bit further. So, get e, I'm going to leave that named value even though it's slightly confusing. But instead of a Boolean, we will return a v, which means that call that subtree get, and change that to subtree get. We'll return a v. If subtree is null, that means that wherever that key would have been, it doesn't exist, so we can return null. If data left equals the value, then we should return subtree dot value left, and here we should return subtree dot value right. And here, not subtree contains, but subtree get. And other than that, it is identical. Questions? All right. So for the programming assignment, which is due a week from today, is that the one that has a lookup table for labels? Well, that's pretty cool. Website's down, I guess. Yep, website is down. So I have no idea. Let's see. This would be 5? which would be a week from today. Thursday, 19th of July. Okay. Yes. Implement a binary tree that acts like a map or dictionary. Not labels. Variables. So this involves making store and load act on strings and not ints. So you end up having to overload do load. There are multiple ways to handle do load. You can have one that just figures out whether it can be interpreted as an int or only as a string, and decides that inside do load, or handle that in the big long if statement. Your map should be called, the class name should be symbol table, and like it says down here, string and integer replace the placeholders from the generic when you actually create the instance of it. We talked about add, we talked about get. Okay, so this is actually, you should use an array as the data storage mechanism for this project. Not concerned with efficiency and looking things up. So if you add something, just add it to the end of the array, and to get something, just look sequentially through the array. Which really doesn't do a whole lot in terms of tree-like stuff. Depth is really the only interesting one, which you can just do math.log2 of size. And the next assignment will improve on this and make it a little more tree-like, I think. In order to make this useful, we have to... Does that make sense? Yes. Hang on. No, this doesn't make sense. Oh, yes, it does. Okay, so private instance variable in machine, just like messages in runtime, you don't need to create an accessor and mutator. This variable is only used from within the machine class. And first thing in your run method, along with your initialization of messages and runtime, you should create a new instance of symbol table string integer. And do store and do load make use of that. So do store will pop something off the stack and create a new, or either add or set the specified key value pair specified by the string that is the operand of the store operation, and the value is the value that you pop off the stack. Load does exactly the reverse action. So if it's a string, if it's a variable name, basically, it takes that, it looks that up in your symbol table and pushes that value onto the stack. Don't worry too much about things like if the thing you're looking up is not in the symbol table, return something reasonable like 0. None of the programs that I run through your simulator will intentionally... All of the programs that I write to test the programs that you're writing are valid programs, aren't trying to do anything stupid. And the main method I think is exactly the same as the main method for PA4. Don't worry about this initialize a message queue and a runtime. That's in there from before I edited these and figured out how the message queue and the runtime were actually going to interact with all the machine stuff. Originally, I wanted them to be in the main program, but that just made things too complicated. So unless there's something preventing you from using the same main class as you used for PA3 and PA4, use the same main class as you did for PA3 and PA4. Any questions? So PA4 is due tonight. I won't be grading it until Saturday. Any questions on that? Cool. All right. Well, I think that's enough material for today. I'm exhausted.